Hi, my name is Ronald Wilson. I'm with the Florida Institute for Cybersecurity Research at the University of Florida. Today, I'll be presenting my paper titled REFICS, a step towards linking vision with hardware assurance. The primary goal of this paper is to release a large-scale dataset with open research themes for collaborative research between the hardware assurance and the computer vision community. Modern hardware devices like integrated circuits are very complex. They're basically billions of logic gates arranged in a three-dimensional structure with each layer performing a particular function. Although complex, they're easy to acquire and present in almost all day-to-day electronic devices. However, the complexity coupled with the ease of access has made them a prime candidate for malicious attacks. These attacks, also called hardware trojans, are basically modifications of existing structure in the IC. Presence of these modifications threaten the security and privacy of the end user. Hardware assurance ensures trust in the IC by verifying the design using approaches like reverse engineering. Now, moving on to the relevance to computer vision. In the context of computer vision, the problems in hardware assurance can be broadly classified into four types: low-level vision, high-level vision, data manipulation, data assessment problems. The low-level vision problems is based on the limitations of existing image processing pipeline in hardware assurance. The existing pipeline simply denoises and segments the image and vectorizes it for comparison with design. However, this assumes that the images are flawless. The scale of the features in IC/SM images may only span a few pixels. With noise and other factors affecting the quality of the image processing pipeline may produce ambiguous results. Resolving each ambiguity would require several hundred hours of manual verification. An easy way out would be to ensure high quality images, but this also means inflation in image acquisition timeframes. The scale of the features ensures that the multiple images of the IC needs to be taken to have a feature resolvability. With existing approaches in hardware assurance community relying on simple methods like cross-correlation, artifacts such as stitching errors would happen. This also extends into 3D when the individual layers of the IC needs to be aligned. The second task is based on the existence of various IC vendors and node technologies. Every IC vendor has their own type of unique features for each layer. This issue requires the approach designed for a specific IC to be generalizable to other ICs as well. We tested the generalization of several algorithms across layers and nodes. Most approaches did not generalize well to unknown designs and node technologies. Also, obtaining ground truth labels for each pixel in the image for every new IC, vendor, and node technology encounters infeasible. The semiconductor industry relies heavily on confidentiality to protect their design rules and leverage from public exposure. With the consequence of each such exposure being compromised devices and stolen intellectual property, the concern is well placed. However, this severely limits the possibility of data sharing and possibilities for future advancements of the research field. This is a prime motivating reason behind using a synthetic workflow to generate images for our dataset. Currently, image quality metrics are limited to intersectional reunion, structural similarity, and mean squared error. These fail terribly when it encounters hairline segmentation errors. These errors change the functionality of the circuit but provide high quality scores. Also, most of the existing knowledge in hardware assurance comes from experience reported case studies. There are several instances where the study was interrupted by unknown issues, resulting in anomalous data and required human intervention to resolve. Detecting anomalous data in the image acquisition phase is very important. With the majority of the layout design generated from repeating patterns, the anomalous data can be reconstructed with techniques such as image painting. Now moving on to the dataset. The dataset currently has over 800,000 images collected from all major layers in the IC from two different node technologies. These can be used as a common benchmark for novel algorithms and help develop end-to-end computer vision machine learning approaches for hardware assurance. To ensure that simulated data is robust and representative of the real world, all existing noise sources and models were taken from literature. Some of these noise sources are modelable while others are random. Noise sources that cannot be prevented or suppressed were added to the simulation model. The SCM produces a single channel grayscale image with the intensity of each pixel representing the properties of the material. The SCM directs the scanning beam towards the sample under study, and the sample in response releases electrons towards the detector. The pixel intensity value is a scaled response in response to the number of electrons received in response to the scanning beam. This is a simulatable process. We use the layout image along with the beam interaction models and the noise models to generate the synthetic SCM image. The model was validated in comparison with the real SCM images using the image histogram image texture. Also, the benchmark results reported by existing image processing works in the field with real SCM images was comparable to the synthetic images. In light of these observations, we believe that synthetic SCM images are a good proxy for real SCM images, but with the added advantage of on-demand samples from specific designs and noise sources. Thank you. Any questions?